Hello, Astronomy, and welcome to our introductory class for the year. So normally this first lecture would be in person. Since we are clearly virtual right now, this is a pre-recorded video. The way that I usually do lectures in here is I just go through a series of pictures and I just sort of talk about them. This is the first lecture for Unit 1. If I were you, I would probably have a piece of paper handy just to jot down any notes that you might want to write down from each picture. So let's just get started. So this first picture, I begin with this one for a reason. This is called the Hubble Ultra Deep Field. This picture was taken over a course of 11 or 12 days in 2003 to 2004. This is, at least when it was taken, the deepest picture into space that has ever been taken, at least again at the time that it was taken. The analogy for this picture is if you were to take a straw, like a drinking straw, that was about 2.5 meters long, so a very, very long straw, and looked at it in the sky, you'd be looking at about the same area as what's in this picture, all right? So you're looking at a very, very, very small sort of like inset of the sky, and this is what you see. Now this picture was taken over the course of about 2 weeks, so it's over almost 1,000 exposures overlaid. But look at what you can see. You can see, if you could count them, you're looking at about 10,000 galaxies. And what's also interesting about this picture is that if you look at the region of the sky the Hubble was pointed toward when this was taken, is pretty dark. Like even with the telescope, you can only see maybe a handful of stars, but this is what's actually there. And if you click on this link, which I know you can't click on the link right now, it takes you to an article, but it has a version of this picture that you can zoom in on. And when you zoom in, I mean, it's just the number of galaxies is staggering as to what's really in the sky. Just for fun, let's zoom in. Let's find a spiral like our Milky Way. Here's a spiral like our Milky Way. So the Milky Way contains a couple of 100 billion stars, of which our sun's only one. Our sun's a pretty average, actually sort of on the small side of stars, nothing that special about it in terms of stars, except for the fact that obviously our planet orbits it. But our sun could be a star, say, right here in a spiral galaxy. Zoom out on that and look at all the things that are around us. And this is looking at a portion of the sky. Again, take a 2-meter long straw, look through that. It's a tiny portion of the sky that the naked eye sees as dark. And I picked this picture as the first picture of the year for a reason. One, it's going to sort of put us in our place. And we think of our own little world as being the center of everything, and in actuality, it is not. We're but one tiny speck of light in the sky. But it also sort of raises the question, and this is a question that we sort of carry on throughout the entire class. And this is a very deep question, but it's what is existence? Like, what is everything? What are we? What are we made of? What is the universe? What is existence? And to answer that question, we're going to begin. And this is a question that we answer throughout the entire semester. We're not going to answer it today. It's important to put ourselves in our proper perspective, and that is that we are, again, a tiny little speck in the cosmos. The second picture that I have for you, this is a picture taken in, I believe, 1990. That little light blue dot is the Earth. This is the most distant picture ever taken of the Earth. It was taken from the probe Voyager 1. The two Voyager probes, Voyager 1 and Voyager 2, we'll talk about in a later unit. But they are the most distant man-made objects that are out there. They've officially left the solar system. But in 1990, they were launched in, I believe, 1977. In 1990, they turned the probes back and pointed the camera back at Earth into this picture. This picture is nicknamed the pale blue dot because that's, everything that you have ever known is on that pale blue dot. And actually, well, in 1990, I was 10. So assuming that I was on the right side of the Earth when this picture was taken, I am technically in this picture. But again, everything that we've ever known, seen, or heard on Earth is in this picture, right? And it's one tiny little pale blue dot pixel from my camera on Voyager 1. So I began with those two pictures. Again, one, to set the stage for the class, but two, just to put ourselves in our proper perspective. Now, moving on. So one important concept that it's useful to have about the night sky is that we don't live with the night sky, to be honest. For most of human history, really up until 100 or so years ago with the invention of electricity, you know, for half of your existence, unless you're asleep, I guess, you lived with the sky as it looks over here, right? You know, we think about how ancient peoples, you know, saw stories and constellations, and how, you know, how they saw, you know, a fish in Pisces or whatever. Well, we don't see the sky like ancients saw the sky, which is actually a huge shame. Due to electricity and lights, we see the sky. I mean, here's inner city, suburbs. Most of us probably see the sky somewhat like this. You know, you can see a decent number of stars in the sky, I guess, but there are about 6,000 stars that you can see with the naked eye if there's no light pollution. And light pollution is the term that we give for light from street lights or glare or whatever, from man-made purposes. You know, in the ancient times, unless you had a fire, at night you saw this, and you lived with the sky. You recognized the patterns. You understood what a solstice or what an equinox was, based upon what the sun or the moon or the planets or the stars were doing in the sky. That kind of experience we don't have anymore, due to electricity, which is a shame. This is a famous picture taken, I forget where it is, it's somewhere up north, where there was a blackout. Obviously this house must have a generator because they do have electricity, but this was the way these people normally saw the sky at night. But when there was a blackout, there was no electricity, obviously no light pollution. This is what they actually saw. And this is an arm of the Milky Way. Like, you can see an arm of our spiral galaxy in the sky, like a milky smear across the sky, which most of us have never ever seen, which is, again, it's kind of a shame. This picture shows, so one of the problems with light pollution is street lights. And you know, you can look at the different designs of street light. This is the best. And obviously in terms of light pollution, this is bad, but it's also wasteful. Like, we're spending electricity, you know, to light streets at night or whatever. And if half of your light is going upwards into the sky, then it's not being used to light your streets. There are actual societies that have been founded to help fight against light pollution. And you can see the best sign would be one where you have like a hood that, you know, reflects all the light back down. This is a picture from space, obviously showing the Earth or showing the United States. And you can see, you know, any light that you can see here is light that is wasted because it's getting into space. What I want to do now, I want to show, this is about a 5-minute video on light pollution. International Dark Sky. A couple places where I want to actually
live on the surface of a planet, spinning on its axis once every 24 hours. Its rhythms of day and night are embedded in the biological makeup of all life. During the day, we bathe in the glow of the sun. As night approaches, darkness takes over. It's a time to rest, to rejuvenate, to marvel at the beauty of the night. Until just over a century ago, our night skies were very dark. Now, even the wilderness is invaded by light. Our cities glow at night. Buildings are lit up. Unshielded lights blind us as we travel along our streets and roads. All these artificial lights overpower the darkness. The waste of energy is obvious, even from space. Much of that yellow glare the astronauts see comes from streetlights. They produce most of the light pollution on the planet. is scattered by the atmosphere, creating sky glows over the landscape. We are losing the dark of night at the speed of light. Light pollution threatens the health of every living thing on Earth. Lights at night disrupt plant growth. Unshielded lights contribute to the deaths of countless land and sea animals each year. Migrating birds crash into illuminated buildings. Newly hatched sea turtles mistake the glow of electric lights for the shimmer of the ocean's surface. Bright lights at night also directly affect humans. Drivers and pedestrians temporarily blinded by poorly designed lights have suffered tragic accidents. Light pollution poses a silent threat to our health. Exposure to light at night disrupts the circadian rhythms that regulate our sleep cycles. People working at night under bright lights or living in light-polluted cities face a higher risk of developing diseases such as breast and prostate cancer. Here is a night sky with typical light pollution. On a good night, only the brighter stars and planets pierce the glow. This is what the night sky might look like if we could remove the light pollution. That faint band of light stretching across the sky is the Milky Way, our home galaxy. Because of light pollution, many people have never seen it. Astronomers know all too well the problems caused by lighting up the night. They need clear, dark skies to study the many fascinating objects in the universe. Light pollution simply washes out their view of the cosmos. Lighting up the night sky wastes money and fossil fuels. To keep a 100-watt light bulb turned on every night for a year takes the equivalent energy output from burning half a ton of coal. Multiplied by the billions of lights blazing up from Earth, the cost of energy we use to light up the night is colossal. While lighting is needed, there are some simple things we can do to ensure that it's neighborhood-friendly, energy-efficient, and helps preserve dark skies. We can replace light fixtures that send light up to the sky with ones that direct light down, exactly where we want it. They're called fully shielded fixtures. We can also illuminate only the places that need it. And of course, we can just turn off unnecessary lights. These are smart ways to use lighting. They offer simple solutions to problems caused by light pollution. We have a choice between wasting resources by sending light to the sky or learning to use light more responsibly. Light pollution is a problem each of us can help solve. Together, we can bring back the dark of night to planet Earth.
All right, so, I've taught this class for a while now, and usually it's typical where I have students go from never having heard of light pollution to like being outraged that we actually waste that much electricity sending light into the sky for needless purposes. Anyway, okay, so switching gears for a minute. So this is a picture. This is obviously a time-lapse picture showing, this is the sun, showing what the sun does over the course of a day. And you probably already knew that the sun rises in the east and sets in the west. So let's just talk for a minute about motions of objects in the sky. So again, this is a picture where you would go out, once an hour, take a picture. Here's sunrise, and then over here would be sunset. And notice the sun makes an arc in the sky. Now it looks as though, or seems as though, the sun's going around the Earth. We obviously know it's because the Earth itself is spinning. We're going to get into those ideas in a later unit, actually a later section of this unit. But anyway, forgetting about all that, so the sun's making an arc in the sky, all right? At some point it rises above the horizon, and at some point it goes below the horizon. So if you were to watch the sun's motions every day for a year, you would notice that there were patterns. First off, the size of the arc changes. Sometimes the arc is very low, like this. Sometimes the arc might be very high in the sky, like this, all right? You would also notice that where the sun crosses the horizon changes. If it's a equinox, the sun rises due east, sets due west. If it's a solstice, the sun rises either north of east or south of east and sets north or south of west. So if you were an ancient person and you saw the sun rise and set, actually you could do this now. You don't have to be an ancient person. You would notice that the pattern changes. Where the sun crosses the horizon changes, and the height of the arc also changes. This is another time-lapse picture showing these are stars rising in the east, setting in the west. You would also notice that there are some stars that form a circle in the sky. They never set. The center of the circle would be the North Star, Polaris. Stars or constellations that seem to circle Polaris are called circumpolar constellations. And again, it's because they never set below the horizon. Okay, so at this point, we need to discuss a couple vocabulary words. The reading goes through these terms, but the reading can be a little bit dense at times. So here I have an individual who's on the Earth. This person's facing north, right? Then I have east, I have south, I have west. You know what the horizon is. That's not a new word, hopefully. So the word, the zenith, is just the point directly above your head. And the nadir is the point directly beneath your feet, or nadir. Did I say nadir? Nadir, sorry. The point directly beneath your feet, all right? The meridian is a line. If you're facing north, the meridian is a line that goes up from the north, over your head, and down to the south, so behind you. So when objects rise in the east and set in the west, they always cross the meridian at some point. The polar axis is just if you had an imaginary line that pointed toward the North Star. All right, everything in the sky seems to rotate around the polar axis. Okay, so the sun makes an arc in the sky, breaks the horizon to the east, rises, crosses the meridian at some point, might be down here, might be up here, and then sets in the west. Okay, there are many different sort of systems to use to find things in the sky. The reading's going to discuss right ascension and declination. It's kind of complicated. The simplest one to use is the altitude azimuth system. So your altitude is just your degrees above the horizon. So from 0 degrees would be at the horizon to 90 degrees at the zenith. And the azimuth is how many degrees you are from north, all right? So let's say you had an object, you need to find it in the sky, you need to report that these two coordinates, the azimuth and the altitude. So if you're facing north, the azimuth is 0. If you turn to face east, the azimuth is 90, south is 180, west is 270, all right? So an object on the horizon, east, would have 90 degrees azimuth and 0 degrees altitude, all right? So what if you're looking at, say you're looking at this object right here, which in this picture is the North Star. The azimuth would be 0 because you're facing north. The altitude, it looks like it's about 45 degrees, give or take. If you're looking at an object really, really high in the sky that is south, well, if you're facing south, what's your azimuth? If you're facing south, your azimuth would be 180. And if it's way high in the sky, it might be 80 degrees. Directly above you is 90, okay? So altitude tells you your angle above the horizon. Azimuth tells you how far you are from due north, all right? And again, you go 0 is north, and you go eastward from north. So east is 90, south is 180, west is 270. This is a diagram just showing the different paths the sun takes in the sky. So on an equinox, which we'll discuss equinoxes later, the sun breaks the horizon due east, crosses the meridian here, sets due west. In a solstice, the sun's arc in the sky is very low, if it's a winter solstice rather. In a summer equinox, the path would be north of east or west where it breaks the horizon, okay? And again, if you go outside and look at this every sunrise or sunset or throughout the day for a year, you're gonna see the path of the sun changes in the sky. So this is a time-lapse video, and I'm gonna go ahead and start it. I want to make sure the sound is turned down so you can actually hear me talking. So this is a time-lapse of sunsets from the summer solstice to the winter solstice. So this is in Seattle, so you're looking west right now. So we just passed the summer solstice, so the sun is setting. So if this is due west, the sun is setting north of west. And notice as we go through the summer months, away from the solstice towards an equinox, the sun is setting closer and closer to due west. And this is something that, you can go outside and look at where the sun sets every night for a year, and you'll notice this. Here we're approaching the fall equinox, which is September 20-something, depends upon the year. You see the sun's moving southward in the sky as to where it crosses the horizon. Right about now, here we go, the fall equinox, that would be due west. As we go past the fall equinox, we're getting towards the winter solstice, the sun's moving further and further south. And once we get to the winter solstice, which is in December, we're getting there. You'll see it at its furthest southern point in the western sky. Which is right here. It was on Christmas Day that year. And at this point, the video stops, but at this point, it would start moving back towards the north in the western sky. This video is kind of cool. This is a year's worth of sunrises. And you can just see where the sun's crossing the horizon is moving. In this case, it's moving, I'm not sure if we're facing west or east here, but you can see it moving along the horizon until it stops and then starts moving the other direction. Right? So these are patterns of motion in the sky, in this case the sun, that you can observe over the course of a year. This last time lapse that I want to show, this is really interesting because you probably already know. I'm going to skip ahead. Actually, you know what? No, I'm not. I'm just going to talk during it. That in Antarctica, in their summer, which would be in our winter at the South Pole, in this case Antarctica, for a period of time, the sun never sets. The sun is always in the sky, so it's daytime 24 hours a day. It's daylight, I should say. So the question I want you to ask yourself before the video starts is what shape, what pattern would the sun make in the sky if it never sets, if it's always in the sky? The Earth is still turning. The Earth is still spinning on its axis. The sun is not motionless, but it doesn't go below the horizon. So this is going to show kind of like the ones we just did at the time-lapse video of the sun's motion in Antarctica, and in this case, I think it's in December, and there's summer. Okay, so here we go. Here we get started. Say we started at noon. Now the sun's moving down. It's going towards the west. The sun sets in the west. At some point, normally the sun would cross below the horizon and it would be gone. It'd be nighttime. In this case, though, it doesn't. All right. Midnight, it should be dark outside, but it's not because the Earth is tilted toward the sun. In this case, 24 hours a day. So in this case, it starts moving up again, and you would get sunrise. You'd get daytime at some point where it crosses the horizon. The clouds aren't being very helpful, are they? They're going to go away in a minute, I promise. There we go. And you can see the sun. Here we're at noon again. The sun moved upwards in the sky. Now it starts arcing down in the sky again. So the answer to my question was, what shape would the sun make? The sun makes kind of like its waves. It rises and then it sets. Eventually it would be below the horizon, but it's not in Antarctica in the summertime. So it just starts moving up again. So you get what looks kind of like ocean waves going up and down throughout the day. Now, this is the last slide that I want to talk about today for Unit 1. And this is a picture showing there's a bunch of stars. You can see lots of stars, but it also points out Saturn, Mars, and Venus, things like Regulus are stars. These are planets, Venus, Mars, and Saturn. And obviously, we're going to discuss stars versus planets a lot more later. But because the solar system is more or less a plane, like, space is three-dimensional, but most objects in the solar system are on the same plane, right? What is essentially the plane of the solar system, we call it the ecliptic. The ecliptic is a very important word because it's a path, it's sort of like an arc in the sky. Because Earth is tilted, it's an arc, it's not like a flat line. And objects like planets, the moon, the sun are almost always, if not on the ecliptic, maybe a couple of degrees above or below. Because even though the system is more or less a flat plane, you can be like 3 or 4 degrees above the plane. We'll get to more of this later. But things that are on the ecliptic, stars are not on the ecliptic. I mean, I guess they could be at random, but like a star, this star right here, whatever that star is not on the ecliptic. Planets, the sun, the moon are on the ecliptic, right? Whenever you see planets, Venus, Mars, Saturn, they're going to be in an arc like this because they're in the plane of the solar system. Stars could be anywhere. Consequentially, you've heard of the idea of the zodiac, the 12 sign, your sign, the signs of the zodiac. There are, I believe, 88 different officially recognized constellations. The 12 that are in the zodiac, it's actually 13, but we'll get to that later, are the constellations that are on the ecliptic. Things like Aries or Cancer or Libra or Scorpio or Pisces or Aquarius or whatever. Those constellations being on the zodiac means being on the backup. The 12 zodiac constellations being on the ecliptic means that the planets can be in those constellations, which the ancient people, which we would call this, we would call it astrology. We do call it astrology now. That has significance. If Mars is in your sign on the day of your birth, in actuality, it just means that those constellations are in the same plane of the solar system. Of course, they're not they're outside the solar system, but they're on the same plane of the solar system, which the planets are too. We're going to discuss the ecliptic and the zodiac in more detail later, but I want to go ahead and introduce the idea now that the planets, the sun, and the moon are all on this arc in the sky called the ecliptic because they're in the plane of the solar system. Okay, so that's our first video. I hope that was helpful, and I will see you guys next time.